3 to 4. So I sent her a message, and I also reminded her yesterday and even today. If she joins, fine. Otherwise, I will start the session. I will take the session. Either way is fine.
Sure, sir.
Not an issue.
Sir. So we
yeah,
only 154 participants are there. Let me remind it in the group.
Looks like she has not joined. I'll just give a call to her. Yeah, hello everyone. I think Anindita ji will join. Okay, right? सत्यन जी पिल्लाई सर से बात हुआ था उनका. She will start at 2:15.
Sure, sir.
Okay, so meanwhile, anyway, I think participants also started joining. If there is anything they want to ask, I think they can ask related to the area which I have covered. Okay, right?
Yes, sir. Participant can write on the chat if they want to ask anything.
Yeah. So anything in the chart, I will see messages. Okay, so one thing, okay, let me see. Okay. Yeah, I'm just sharing a screen just to discuss about what I've done so far. Okay, here you can see I have started with the classical memory and then gone to quantum qubits, spin-half systems, photon polarizations, trapped atoms and ions, artificial atoms using electronic circuits, semiconductor quantum dots. Basically, those things we have briefly discussed. We did not go into the details. Okay. And then, okay, just a minute. Yeah. And then after that, Anintha is supposed to take quantum advantage claim, the roadmap for future, but due to some other last minute engagement, she has to ask for alternative time. So that is today at 2:15 to 3:15. Okay. And yeah, with that, okay, after that, I was supposed to start single and 2 qubit gates, Solovey-Kitow's theorem. We discussed that day, 2 to 4. Okay, then quantum correlations and entanglement and Bell's theorem. Ritajit took that. Okay, right? And then Jinesh sir has taken, I think, Turing machine review or Turing machine complexity classes. Okay, space complexity. And then Anand Ramanji took reversible computation, universal quantum logic gates. Basically, reversible computing with electronic circuits could be used as a base to understand the quantum gates. Okay, so he took that. Then I started after that quantum parallelism, quantum algorithms, particularly Dutch algorithm. Okay, Dutch Joyce algorithm. I'm sorry, the spelling is other way around. Okay, and then Bernstein's Vajrani algorithm I discussed. Simon's algorithm yesterday, I think day before yesterday, Jay Kumar has discussed. And Ritajit discussed yesterday Grover's algorithm. Okay, and today and tomorrow, Mustafizur from IBM supposed to discuss gave a session on quantum Fourier transform and prime factorization, the applications of quantum Fourier transform using Shor's algorithm, which is actually a threat to existing RSA encryption. So those 2 days he's supposed to cover that. Due to his health reasons, he could not start today and tomorrow. So those 2 days, that is today and tomorrow, I would engage. Within that 1 hour, Aninditaji would take. She would be talking about quantum advantage. Okay. And the QFT and Shor's algorithm would be on 30th July. That is Friday. And sorry, it's not a Friday, it's Wednesday. And sorry, not Wednesday. 31 is Thursday and 30 is Friday. Yeah. So 30 is Wednesday and Thursday. They will discuss. Okay. And so my parts would come over here. I would discuss the HHL algorithm and quantum error correction. Basically, HHL algorithm, before that, there is something called quantum phase estimation algorithm that I will discuss today. Okay. Tomorrow, I will discuss error correction, quantum error correction, and the codes and HHL algorithm I'll discuss. Okay. And then on 28th, that is Monday, Jay Kumar would discuss the quantum complexity classes, where exactly the quantum computing would lie on the complexity class discussed by Jinesh sir earlier, you see. Okay. And where exactly quantum would lie, that he will discuss. Okay. And then one of the algorithm which is very much important for finding the eigenvalues of a matrix, that is variational quantum eigensolver. So that would be discussed by Raghav on 29th, that is Tuesday. Okay. And like I said, Mustafizur would take QFT on Wednesday. On 31st, Thursday, he would talk Shor's algorithm. Okay. On 2nd, that is on Saturday, the last session. Okay. 2 to 4, Dr. Santosh Viparthi from IIT Ropar, he would talk about some quantum computer vision. Okay, right? So that means that would be overall concluding session on August 2nd, followed by valedictory for a half an hour. Professor Pillai sir would take over. Okay, so this is what QT-05 is. Okay, I think Nindita ji, I think she is going to join, right? She would talk about quantum advantage. Satyen sir, you would introduce her.
Yes, sir.
You have the introductory plan, na? Introduction to her.
I'll ask if you have, you can share it.
Oh, you have not
suggest
planned?
it. No, so I have not planned it yet.
Ah, okay. Okay, okay, okay.
Or if you have, sir, I mean, you can introduce.
Okay, wait. I think she said.
So that schedule is already there. So one has asked in the chat that schedule should be shared in the QT-05 group. It is already shared earlier. You might have joined later on, so let me forward it again. It is already there.
Yeah.
I've shared it again.
Okay, she's asking for a password. I'll just share the password. QTQCP, right? QT.
Yes, sir.
QCP. Caller. Looks like not able to join. She has joined. Yes. Hello, Anindata ji.
Hello, hello, sir.
Yeah, we can hear you and yeah, loud and clear. Okay, so then I think we can start. Let me stop sharing. So I was just discussing about the schedule and all. Okay, I think we can start exactly. Okay, so
Okay,
once
thank
again,
you so much.
yeah, Satyanji, I'll start.
Yes, sir. Please go ahead.
Yeah, yeah. Okay, so very good afternoon to all the participants and the organizers. It is my privilege to introduce to you the very energetic speaker in the domain of quantum computing, Dr. Nindita Banerjee, and currently she holds a like a designation of adjunct scientist and project manager at the CDAC Pune. So her specialization is in quantum computing and quantum communication, right? And she also appointed as an expert to India-US Critical Emerging Technologies Initiative, that is ISET, recognized by IT and launched jointly by India and US in leadership in 2022. And she is also expert committee member for this AICTE UG minor program. So we proudly say before that she was also one of the committee member for our minor mentoring group for our minor at our institute. So before joining here, she was one of the lead pioneer in QNU Labs, Bangalore. So the QNU Lab is currently holds a very good position in Indian quantum domain. So she has done her part in that. So without wasting further time, there are so many credentials on her profile. So you are welcome to check on our LinkedIn and our Google Scholar. So I would request Dr. Anindita ji to take over and enlighten us about the quantum advantage. Over to Anindita ji. Please carry on.
Sir, can you see my slides?
Yes, I can see. Yeah, we can all see. Yes.
Yes, sir. Visible.
Yeah.
Yes, ma'am. Visible.
Thank you. Welcome, everyone. Thank you, Dr. Ashut Babu, for the kind introduction. And without, spending more time here, we will jump into the discussion topic, which is the quantum advantage claims. A very interesting topics, because we are not talking about today on quantum computing. Basics, information, algorithm, all is done and covered in the course. So it's a good time to talk about what is the advantage it can give us. When we talk about quantum advantage with respect to quantum technology, then based on the different domains, the advantage changes. It can be, if I'm looking from computing, it can be a speed up, it can be discovery, it can be many things. But when we're looking into communication, then QKD can also be considered as an advantage. And when we're looking into sensing and metrology, accuracy, precision, so it all depends that how, so what is the advantage I'm getting out from this particular technology domain. But here we will restrict ourselves mostly to the popular understanding in the quantum computing domain. So I will begin the presentation with the criteria, the 5 essential criteria for a quantum hardware. Because if you're talking about computing, the realization of a quantum computer is very critical, is essential to obtain any kind of advantage, which comes. Some of them will come from the faith of execution of the quantum system, and some of them will come from some validation with respect to brute force attack on a classical simulator. So the five criteria for quantum computer, a realistic or a practical quantum computer would be, the first one would be the well-defined qubits. What does it mean? That a scalable physical system with well-characterized qubits. So it should have clearly identifiable qubits with known physical parameter. Now, what does that mean? If I'm talking about, because last conversation I had with you, everyone here was on photonics based computing and communication. So let us just say with respect to, relate this with respect to photonic qubits. So from that perspective, if photonic qubits can be encoded using various degrees of freedom, polarization, path, orbital angular momentum, time bend frequency, path encoding, when we say it is transmitted, it is logic 0, it is reflected, it can be logic 1. So a clear, it should be clearly characterized with the degrees of freedom. Then qubit initialization. We should be able to initialize the state of the qubits to a simple reference state. Say, you must have seen in all the Qiskits or in a simulator, we start with 0, get 000. So this provides a clear starting point for all quantum algorithms. Now, this is critical because we know the wave function collapse, the superposition, the entanglement on measurement, everything, we lose the state. So this becomes a very important criteria. For single photon sources, we can combine it with a spatial demultiplexer, which can generate well-defined path-encoded qubits. But this is again, in photonics also, there are different ways, different degrees of freedom, different photonic states. It depends. It is very specific to the nature of the quantum hardware. Then comes the long coherence times. So coherence time, the stability, it is very essential. I'll just put it in one sentence. The stability of the qubit should be longer than the gate operation time. If it is comparable to the gate, then you cannot have more gates applied on the circuit, which means you will not be able to do any complex quantum algorithms. So coherence time plays a very critical role in the selection or realization of a quantum computer. In photonics, we have the privilege because we use photonics for quantum communication. So in free space or optical fiber, they can maintain coherence over long distances. Again, depends whether it is on free space, it is polarization, or it is phase encoded. So there are a lot of factors to be considered. Then universal gate library. Last time we had discussed about the when we're talking about the quantum computer, single qubit quantum computer, I showed you that how we realize a classical NOT gate using a transistor and how we realize it on a using some optical gadgets. So any computing, we need a universal set. For example, you have NAND, you have AND or logic gates. Similarly, if you say 3 qubit, then Toffoli, which is also called as Feynman gate. Then you have the CNOT gate. So you should be able to realize some basic universal gate library set. Then qubit specific measurement, the ability to measure the qubit without disturbing others is very essential because they are very fragile and they have a tendency to interact with the environment and the neighboring qubits. So quantum qubit measurement is very critical. So when I'm talking about these aspects, so we know that still quantum hardwares are in development, and we're talking about error correction, fault tolerance. So each and every point is a challenge. And to realize a quantum advantage in quantum computing, we have to realize it on a hardware which through which we can verify the state, which is stable, and we can compare different hardwares with respect to these 5 criteria. Now let us go into the building block. So considering that quantum computing brings together quantum mechanics and computer science, so for providing a reliable readout of computational results. So we would say that if I'm comparing, so here the comparison is already given, and I don't want to get into what a qubit is or how do we realize these gates. Basically, when we talk about any quantum circuit, it is qubits, gates, circuits, algorithm, error correction. All of them depend upon the nature of quantum hardware technology. But basically they are the things which most of the students or any user would be familiar with. Now let us look into the structure which we usually don't talk about except the computer scientist or when we are building a quantum a computer, classical computer architecture. Here you will see a queue added to it, but let us talk about a classical computer first. Here we divide them into different layers. The lowest layer will always be a quantum hardware or a classical hardware. Then you will have the microarchitecture, you have the arithmetic logic unit, runtime compiler. So here there is the structure for quantum is nothing different but just adding a queue to it. So then we start with the highest level, which is the quantum algorithm. We still do not know what kind of quantum algorithm would that be if I'm talking about a practical unit, but say some sort of quantum algorithm will be there. We already have a lot of theoretical algorithms there. We are simulating them in classical simulators. So fine, some algorithm is there. And then we need a program that which we do classically. We can use programming languages like C++, Fortran, and these languages can produce code for a classical processor. But now we need a quantum language for quantum processor. And one such example is, say, Project Q. It is open source software, and it is implemented in Python. I'm sure you must be familiar with this through this course. So now every programming language will now have a compiler. Now it takes the input from the arithmetic logic and converts it into a low-level language, that is a classical assembly language. So in quantum, we have a QASM. The QASM was developed by Nielsen and Chuang. This this is the basic textbook through which we all have educated ourselves in quantum computing and quantum information. So he used it to generate quantum circuits. And then we have the quantum arithmetic layer, which is again very different because the maths of the gates and the qubits are different than the classical ones. Runtime, I'm not very clear about the runtime part, and it will be gradually defined. Compiler we have discussed, arithmetic we have discussed. Then we go to quantum instruction set architecture. So fine. I mean, the instruction set again from here, it's a very traditional one, but again, all these logics, the nearer we go towards the quantum chip will again depend upon the kind of hardware we are trying to use. And thereafter, we will go to the microarchitecture. So the layer from microarchitecture to the quantum algorithms up is all digital, but the layer from the microarchitecture to the quantum chip is all digital. Okay, because it mostly comprises of controlling the qubits, maybe using some physical signal like microwave microwave signal to control the quantum entity there, which can be anything. I'm talking about ion trap or superconducting qubits, right? And so this microarchitecture plays a very important role, and again it is a very specific to the quantum hardware. So you can see that the structure is almost, the framework is same, but it again depends. But since the quantum mechanics is very different from the classical, so that way the structures are redefined. Some of them, but most of them, I cannot even take one example, right from compiler to arithmetic to the ALU unit to the microarchitecture, everything is very different. So, and finally, I would say, if you're talking about the quantum measurement part, in classical, it is, one-time measurement is okay. But in quantum, we have the wave function collapse. So we have a probabilistic measurement. So if, in case of any quantum measurement, if we do 1,000 times, we will get different results. So later we make a histogram. That is what we do. We make a histogram and of what has been computed, and the readout, which has the highest frequency of occurrence, will have the highest probability. And that will be read out from an architecture, and that will be published as a result. So the architecture is different, the building blocks is different. And then now let us straight away jump to the applications. So I love reading this report. It was published in 2021, and it kind of divides the applications, the different kind of applications with pre-fault tolerant era and a fault tolerant era. So when I was reading this, the D-Wave had published about 5,000 qubits. So gradually it will scale up, but still, shall we go to this era fast? May or may not be. It all depends upon the technologies from different aspects, right? So it is not a very smooth transition. There might be at some point of stage a qubit identified which is better than superconducting qubit, and that may lead to formation of a quantum computer is very well a probability. Then you can see different applications here. Supply chain optimization, self-driving robots. So they all are dependent on a universal quantum supercomputer with some 10,000 logical qubits. But does that mean that we cannot experiment with these applications here in this pre-fault tolerant era? Of course we can, but it will not give me any meaningful comparison. And at this point of time, they will be, it will be very much part of our life. So now, if I want to talk about, say, quantum advantage, We will say that the enhanced precision of computation over classically intractable problems that currently need to be solved approximately. This is very clear. Then there are advancements in science from the simulation of quantum systems in ways that would otherwise be impossible. Now, this is this is another aspect. Why? Because here I do not have my classical computer supporting or validating the system. And this mostly comes from faith in the quantum computer. So definitely it is something which will happen once we have a fault tolerant quantum computing system. But again, an enhanced precision from what cannot be solved by a quantum computer, or is getting solved by, sorry, cannot be solved by a classical computer, or is getting solved by in some approximate methods, may be interesting as of now. But again, meaningful results, maybe not. And you will see that, I was referring to one of the papers published by IBM, the quantum advantage framework. They have very nicely categorically, discussed the subject in detail. And so basically, we will say something which has a higher efficiency, which is economic. I have some economic advantage. And to understand this economic advantage, I will again refer to you this paper, which every industry with respect to economics, that what is the commercial angle to it, how it is going to the revenue part, or the how it is going to benefit the industry, and it is estimating, it is quantifying the advantage. So that may be of interest as well. Accuracy, yes. So again, the quantum advantage is also a little hyped, but there are several steps we have to go before we reach an advantage. And one such step is quantum utility. So this is a stage, the first part. The first part is actually quantum utility. I would like to read from what the authors have quoted. It's a Nature publication in 2023. For the first time in history, quantum computers are demonstrating the ability to solve problem at a scale beyond brute force classical simulation, where the only alternatives are carefully crafted, problem-specific classical approximation. Okay, so those who learn to harness their capabilities today could be among the first to achieve quantum advantage. So the quantum advantage is not just one step. There are several steps that will lead to this factor. First, of course, we need a good, stable, faithful quantum hardware. And we have just seen, the challenges associated, or the criterias associated with with a quantum computer. Then we saw that, for a quantum advantage, it's a very broad word, and and it is possible, but it is difficult to say whether it will happen in next few years. But the best approach is to go for a quantum utility, where we are trying to compare this with brute force classical simulation. And the paper presents an example of such it's a paper from IBM. And yeah. So there again, they have classified the problem statements for quantum advantage into sampling problem, variational principle, and expectation value. Okay, so we will briefly touch upon these problem statements. And it is not that, everything else may not be useful. See, because when a lot of minds are actually thinking or brainstorming about the different applications, then perhaps there can be some more problem statements which can come up. But at the moment, based on the current research which is going on, you will be able to categorize them into these three classes, broadly into these three classes. Now, if I'm looking at the random circuit sampling, now in sampling problem, We may also like to refer the Shor's algorithm, but it is not entirely a sampling problem. Um, but you may want to, also consider, because it will not be incorrect as well. But we will leave that aside and we will talk about another problem statement under this sampling problem, which is the random circuit sampling. So this involves generating random circuits, random quantum circuits, and we apply them to qubits and then sampling from resulting output probability and from the resulting output probability distribution. So the goal is to compare the output distributions obtained from the quantum computer with those simulated on classical computer. And this is of interest. People have actually Google's claim in 2020 or 2019. It was based on a random circuit sampling experiment. They had used Sycamore to sample from a random quantum circuit, and they argued that simulating the same task on a classical supercomputer would have taken significantly longer. Now, the claim was also discussed in the ecosystem, and let us not get into the arguments over that. But this is indeed a good step, and it shows how promising this can be. But again, it is also important to note that our that it has its own challenges as well. Um, and it is not just a benchmark, but also a topic of ongoing research. The people are exploring the complexity. They are trying to understand the computational hardness and how to verify the results. So again, these are explorations, and it is a good area. The sampling problem is a good area to venture into to explore quantum advantage. And that is how I would put it right at the moment. Now, the second category was the variational quantum algorithms. Now, this has emerged to be a very promising solution. The algorithm has a concept. Now, let me talk about that concept. It is actually about training quantum computers in a similar manner on how we train the neural network. That is, we find the optimal parameter of the model to maximize or minimize some objective function related to the model. So if you look at the framework, so these are the applications here, but let us talk about the framework. It will comprise of, the initialization, then the circuit answers, the cost function, and the training procedure. So briefly, the computer is first initialized in a default state. The circuit answers takes the default state to a target state through a variational operator. And then there is a training procedure in a hybrid quantum classical loop that helps to converge to an optimal solution. Now, this is a very broad, method, and you will see these in the following slides when I'm talking about the problem statements within the variational quantum algorithms. Now, to see where the problems are applied, it's mostly in quantum chemistry, such as calculating molecular energies, optimizing molecular structures of complex molecules. Now, it can also be used in optimization problems. It can be used for machine learning. Those working in quantum AI neural network, they will find this in data classification, pattern recognition. So it serves broad applications, and a lot of research is going also in terms of model development also. So a lot of work is going around it, and I've presented some applications here in the presentation as well. And there is a paper which you can refer to. It provides a review on variational quantum algorithms. So now, as we discussed that, the variation principle We will consider these three areas within that. The quantum phase estimation, variational quantum eigensolver, also known as VQE, and quantum approximate optimization algorithm. So we will delve into these three areas which falls under variational principle. So the first one is the phase estimation algorithm. Now, the phase estimation is one of the first algorithm for ground state problem, and this can solve the ground state problem efficiently time. But it is important again to understand from an advantage perspective about the verifiability of the result. And again, it is based on the trust that the quantum circuit is performing correctly. So here the quantum circuits, the challenge part here for these type of problem statements are, the quantum circuits here are very deep, and they are generally thought to require the fault tolerant quantum computers. So again, when we're talking about fault tolerant, it's very different from the NISQ, the noisy intermediate scale quantum computers, which we all have, which the announcements which we are hearing about establishment of a quantum computer, they are all NISQ category. And again, from a jump from the NISQ category to the fault tolerant, the problem here does not lie only on the computer architecture, but also on the different modular part of it, be it chip, the material, the qubit technology, the error correction, error mitigation, which I'll talk about it at the end. So so a lot of factors goes into. So when when the end goal, the verifiability is dependent on trust, and the circuits are very deep. You may also like to think that the criteria which we had looked in the first slide, which was on the coherence time, how critical it becomes. So fine. So this is one problem. The second one is the variational quantum eigensolver. So this is a classical quantum hybrid algorithm which outsources some of the processing workload to a classical computer to efficiently calculate the ground state energy of a Hamiltonian. So here the VQAE it's interesting to know that it is a low depth. I do not know how many of you are working in this area, but they must have observed that the requirement of qubits and the gates. So it is in fact a low depth alternative for ground state problems, which can be executed on a pre-fault tolerant quantum devices. Now, so because it's very important to understand what all can be done on a pre-fault tolerant era and what can be done post-fault tolerant era, then you can put your energies in thinking about these problem statements, because finally every one of us here wants to have the quantum advantage, right? So fine. So moving forward, it fine. There's so many things we can talk about it, because we are the new of applications. Any review paper you will pick, or any application you will see, chemistry to finance, these are of interest, and it is a good idea, to develop your understanding, or your foundations on this particular area. Then so I hope you understand that the structure look almost the same. That is why it falls under the variational quantum algorithms. You always have the hybrid classical quantum, which I had already discussed. So then we go to the next area, which is the quantum approximate optimization algorithm, QAOA. It is a variational algorithm which has applications for solving combinatorial optimization problems, or on a near term quantum systems. So this algorithm can be used to calculate the so the ground state of a Hamiltonian, and can be easily implemented on any classical simulator. I hope you're familiar with this in Qiskit, in Cirque. So all these, they look the same. They have a classical quantum, but the problem statement differs. The answers will differ. So this combinatorial optimization problem, which I hope you all are familiar with, it involves finding an optimal object out of a finite set of objects. And so again, in NISQ era, this if you want me to go into a little bit of, briefly tell you about this thing, it uses a unitary. It is characterized by parameter beta and gamma, as you can see here. We prepare a quantum state, which is ket xi beta gamma. The objective is to find the optimal parameters, which is given by beta optimal and gamma optimal, such that the quantum state, which is here, it encodes the solution to the problem. So just give me a confirmation that I hope we are in. You can hear me and I'm still connected.
Yes, you are connected, ma'am. Yeah, I think participants also would say the same.
Okay. The unitary here, which you can see here, it is composed of UB and U gamma. And so HB is the mixing Hamiltonian, HB is the problem Hamiltonian. And we can observe that it is similar to the quantum annealing. So I remember one of the problem I was working on, portfolio optimization. And there is, in fact, some good interesting cases where we compare the QAOAs with the annealing, and there are some industry as well who is looking into the financial portfolio problem from a quantum perspective. So this is indeed a good area to look into. Then finally, it is the evidence. You can see this paper, evidence for utility of quantum computing before fault tolerant era. Now, papers like this or the research in this area is actually interesting, and if you move towards the quantum advantage section, because as you can see, it's talking about the utility, which means comparing it with brute force simulation, classical simulation. And adding here, we know that we can simulate till maybe 2030, but 50 and beyond is impossible on a classical system. So that is the reason, if you're looking at before fault tolerant era or pre-fault tolerant era, one must be directed towards quantum utility, which will eventually lead to quantum advantage. Now that's a very important topic, which and this paper, I think if you can read this paper, this also is will give you some directions. Now here they have usually in this area we can consider problems like estimating ground state energies of molecules, measuring kernels of in machine learning. So these are the problem statements which you can consider under this category. Here, simulating time evolution is a classic example of measuring expectation values of short depth quantum circuits. So this is a very strong candidate. And it is important to consider it from the lens of verifiability as well. Finally, we'll talk about the critical elements. This is my last slide. We'll talk about the critical elements for quantum advantage. Now we have been hearing these terms, no? QBER, error correction, error mitigation, error detection. So they are not the same. They are three different areas of work. Particularly, when this quantum error correction, the word is also applicable in quantum communication. But quantum communication is in quantum communication, quantum error correction is totally classical. It is a classical algorithm. And here in quantum computing, quantum error correction is the only quantum part. Rest are not actually quantum. So quantum error correction, it refers to the techniques designed to protect quantum information from decoherence. Decoherence is just one. There are several. I mean, gate imperfection, measurement error, stability. So there are so many factors due to which you will get you will get a very high error. The better you isolate the system, the better you stabilize the system, the qubits, uh, your error will be confined, but you will never have a case where there are absolutely no errors or there are minimal errors. They will be to some percentage. So it's the error correction part plays a very important role in understanding the system as well. Now, this is also the groundwork for fault-tolerant quantum computation. So the quantum computations algorithms can be performed in a manner that is resilient to noise or any physical error rates. Now, physical would mean the computing system, the platform, the qubits, everything. So and there are several error correction codes like surface codes and all which are used, and it's a very interesting area again. Then we have error mitigation. So this refers to the set of techniques which aims to reduce and sometimes I don't know how much, but yes, it eliminates the error basis in expectation values caused by noise in quantum circuits. And unlike the quantum error correction, the error mitigation uses the classical post-processing of noisy output from the ensemble of circuit. So again, this is a different, and again, based on the hardware, the techniques, the methods will be also different for mitigation. I'm sure you must have found this, used in when we are trying to run the Qiskit using a real hardware. So this is something which we also try to find out or try to understand what are the, if we can simulate quantum noise, and if that can help us find out techniques for error mitigation. So that is again a very interesting area. Then error detection, it actually offers an intermediate goal. It uses extra qubits to detect, but it doesn't correct, it just detects. So it uses the error correcting codes with post selection. Which are also subsumed during the error detection, which is very important. So these are the three areas which is very critical for quantum advantage. Now, the reason I have mentioned just three here because I was referring to this paper, but at the same time, we cannot neglect the importance of the qubit, of how the qubit is generated and how stabilized it can be. And when I'm talking about error, please remember that the error here may be confined to just the qubit. But if you're looking at a practical system, the sources of errors are multiple, and how it influences the qubit, the platform, the environment, the stability, everything has an influence on the stability of the qubit. So it is also very critical to attain a quantum advantage, that how much controllability you have on the computing platform, or the quantum computer. So with that, I think we hope that through National Quantum Mission, we will have you will see the quantum computers getting established in India, and both from the benchmark ones and the indigenous development will also happen. And there is a lot of avenues for research, which is actually interdisciplinary in nature, because I had kept on saying that all these problem statements can happen if we have faith, and faith will come from all these five criterias. how we score there, and each and everything, right from making a qubit to stabilizing it to monitoring it, manipulating it, involves lot of electronics, electronics and compute and communication areas to be looked into. That even the communication, how the entire system is communicating with each other, how much delay it is adding, what is the latency of the system, all are very much interdependent. So I think with that I am coming to the end of the presentation. I was thinking that how will I cover this quantum advantage in 1 hour or 45 minutes or so. But I think I have completed it sooner. Um, but thank you again for giving me this topic, because it's very interesting, and at the same time it's not something which one can say that it is going to happen at this particular time, or that something very different can be announced at some point of time, and it can change the game as well. We have to be very careful in identifying the problem statements for which we are, if we want a quantum advantage, because many people in the ecosystem are actually exploring. There are several application areas where a classical computer would be good enough, and we would not be needing a quantum computer. But so whenever you are looking at a quantum algorithm or quantum application, please do consider the advantage part, because otherwise it's of not meaningful. And the advantage from the advantage before advantage, I think quantum utility is something which we should be looking for. And eventually we will have faith in our system, because the technology is growing at in a meteoric speed, and in different disciplines. So each and every discipline has a role to play for making this happen. Yeah, so thank you. I hope I was connected.
Yes, thank you very much, Animita ji. So, participants, if you have any questions, please put up in the chat. I will read through. Ma'am, there is one question here. Okay, what is the honest situation in terms of quantum advantages claimed by various quantum devices like Google and Microsoft, and quantum communication claims so far?
So there are some announcements. I just discussed about the Psycha mode, which carried a 200-second sampling task, which would have taken 10,000 years to complete. So this indicates a quantum speed up, and it was in 2019. Then there was some work on the random circuit sampling. I don't remember. Yeah, Google's qubit quantum chip, which was Willow. It was able to carry out the RCB which I was talking about under 5 minutes. Which would have otherwise taken some septillion years. So that was another announcement. And then we had China, which was using a photonic quantum computer. I don't remember the name. It was some Juan-Hang 2, which was able to implement this Gaussian boson sampling. And that was also talking about a speed up of some septillion times faster than the world's fastest supercomputer. So these are few I know about them. But at the same time, there are a lot of assumptions which we take when we are talking about this, which is not mentioned, right? The connectivity between a quantum and a classical computer. That is why I said the controllability of a quantum computer is going to play a very important role if you want to show advantage. And before advantage, I think utility is again would be a good way to go towards a quantum advantage scenario. Now, coming to quantum communication. Already we know that that in QKD, we are solving a problem which cannot be solved by a classical, conventional classical communication system. So what we are doing is we are generating keys in presence of an eavesdropper, and they are generated spontaneously. In classical, we generate the keys and we transfer the keys through a problem statement to a other party. It is a pragmatic approach, and it can be, many party communication. But still, you have, anybody can copy or clone the state, and you will not be able to know about it. And if there is a problem statement, for example, a quantum computer, which can break the problem in polynomial time, I'm talking about the Shor's algorithm and RSA. So then, it's just that you do not know, but then it is, if you look at the complexity classes also, it's not claimed that it cannot be solved. Okay, so all these things matter, and in quantum, it's a hardware solution. We do not generate the keys prior and then distribute it. The name is not correct, actually. It is not. It should not be quantum key distribution. It should be quantum key generation. So that is itself an advantage. For PQC, see, it's a software solution. Basically, some algorithms, classical problem statements are believed to be quantum safe. For QRNG, you can see the NIST document. The QRNG existed a decade, 2 decades back also, but it's only that today we're talking about optical QRNG, which can give you a high throughput. Otherwise, one in 1970s, they gave you throughput of about, say, 50 bits, and today we're talking about gigabits. So that is a scale.
Okay, thank you.
Question which I can see is on quantum portfolio. What is it, sir? I think there are too many questions.
Yeah. I'll ask some more relevant ones. Where are we in photonic quantum computing as of now?
In photonic computing, there are some startups. I would still say startups globally, and in Indian ecosystem, there is Quantfluence, who is trying to make a photonic chip. But it's a broad area. When I spoke to you, I was talking about degrees of freedom of a photon. Now, there are different ways you can realize a photonic state. Is a squeezed state, or it's a polarization state. There are different ways. So actually, the companies are trying to explore these different qubits, photonic qubit states, for realizing, but it has not gone too far. The challenges are on scalability as well, and on qubit to qubit interaction for photonic devices, because it's very difficult for photons to interact. So the fidelity of a 2-qubit gate in superconducting is better than in photonics. So all these things will again matter.
Yeah. Okay, ma'am. I think we will take a quick break, and before that, let's thank the speaker very much. A lot of information has been shared by Anindita ji. Thank you so much, ma'am. So I hope our participants are happy, and with this, I think they know now why to appreciate quantum computing.
Thank you, sir.
Yeah, there are quite a few questions, and basically some of them were asking about the research direction and the research problems and the material sources and all. So those things are like other participants themselves are sharing. So everything is there. So, yeah, ma'am, one question from my end. So let's say people do talk about the number of qubits when it comes to the hardware based quantum computing, let's say ISC or TFR and some other IITs. So where are we at now when it comes to photonic based quantum hardware? Let's say certain number of qubits we were able to realize, and apart from communication, are we able to do some computing? photonic based one. Yeah, Confluence. Yeah, I did met the people there. So yeah, can you please comment on that?
Yeah. So see, I may not have more information than what you have on Confluence. So I think good things may happen soon. Since we have, I know that they are trying, they are working on it, and the challenge is also said that for a quantum computing architecture, the investment is huge. So in communication, you buy one QKD product for about say 2 CR, but for a computing hardware, it's many scale more than that. So yeah, it's a challenge for them, but I hope they will soon come out with something. They have collaborated with IIT Madras on fabricating of chips. Yeah, I have seen the detectors, heterodyne detectors, but maybe yet to see a qubit.
Okay. Yeah, thank you, Anindya, once again. Yeah, I think participants, I hope you also thanking her, appreciating her. So, ma'am, thank you. You can exit, and I will take over maybe after 5 minutes break. Yeah.
Thank you, sir.
Yes, participants. So it's 3:05 now. We'll start at 3:10. So there was a question on what should be the roadmap for someone with the CS and finance background to contribute substantially in the field of financial quantum computing. Yeah, so there are conventional machine learning influenced quantum machine learning algorithms, right? You can pick and start applying with the existing the data available on the net. Okay, so first thing you can do, you cross checking the accuracy as well as computing time of conventional ML on the data and classic quantum ML on the data. That's what we are trying from quite some time. So that is a starting point you could do. Okay, so if you would see some good computing time acceleration, then that is a very good thing to publish, right? Also when it comes to accuracy also. Yeah. Okay.